Hello everyone, welcome back to the next video. So today we'll be talking about common collections. Rush standard library include a number of very useful data structure called collection. Most other data type represent one specific value, but collection can contain multiple values. Unlike the build in array and tuple types, the data this collection point to is stored on the heap, which means the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and cost, and choosing an appropriate one for your current situation is a skill you will develop over time. In this chapter, we will discuss three collections that are very useful in Rush programs. A vectors allows you to store a variable number of values next to each other. A string is a collection of character. We have mentioned the string type previously, but in this chapter we will talk about it in depth. A hash map allows you to associate a value with particular key. Its particular implementation of the more general data structure called map. To learn about other kinds of collection provided by the standard library, see the documentation. We will discuss how to create and update vectors, strings and hash map, as well as what makes each special. Storing list of values with vector. The first collection type we will look at is vector t, also known as vector. Vector allows you to store more than one value in a single data structure that put all the values next to each other in memory. Vectors can only store values of the same type. They are useful when you have a list of items such as lines of text in a file or prices of item in a shopping cart. Creating a new vector. To create a new empty vector, we call the vec colon colon function as shown in listing 8-1. So basically vector is kind of like an array or in JavaScript, or a list in Java or Kotlin. I think Kotlin has one called mutable list. Note that we have added a type annotation here because we aren't inserting any values into this vector. Rush doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We will cover how to use generics with your own types in chapter 10. For now, know that vector t type provided by the standard library can hold any type. When we create a vector to hold a specific type, we can specify the type within angle brackets. In listing 8-1, we have told us that the vector t in V will hold elements of the I32 type. More often, you will create a vec t with initial values, and Rust will infer the type of the value you want to store. So you rarely need to use this type of annotation. Rust conveniently provides the vec macro, which will create a new vector that holds the value you give it. Listing 8-2 creates a new vec I32 that holds the values 1, 2 and 3. The integer type is I32 because that's the default integer type, as we discussed in the data type section of chapter 3. So this is another way to define a vector. Because we have given initial I32 values, Rust can infer that the type of V is vec I32 and the type annotation isn't necessary. Next, we will look at how to modify a vector. Updating a vector. To create a vector and then add elements to it, we can use the push method as shown in listing 8-3. As with any variable, if we want to able to change its value, we need to make it mutable using the mute keyword. As discussed in chapter 3, the number we place inside are all of type I32 and the Rust infers this from the data, so we don't need the vec I32 annotation. Reading elements of vectors. There are two ways to reference a value stored in a vector: by indexing or using the get method. In the following example, we have annotated the type of the values that are written from these functions for extra clarity. Listing 8-4 shows both methods of accessing a value in a vector with indexing syntax and the get method. Okay, so this is how you can get a value, or you can use the option sum none. Okay. Note a few details here. We use the index value of 2 to get the third element because vectors are indexed by number. starting at 0 using ampersand and square brackets give us a reference to the element at the index value. When we use the get method with the index passed as an argument, we get an option ampersand t that we can use with match. The reason Rush provides these two types to reference an element is so you can choose how the program behaves when you try to use an index value outside the range of an existing elements. As an example, let's see what happens when we have a vector of 5 elements and then we try to access an element at index 100 with each technique as shown in listing 8-5 does not exist. But I think here you get an option, right? When we run this code, the first square bracket method will cause the program to panic because it references a non-existent element. This method is best used when you want your program to crash if there is an attempt to access an element past the end of the vector. When the get method is passed an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of the vector may happen occasionally. Under normal circumstances, your code will then have logic to handle having either some element or none, as discussed in chapter 6. For example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none value, you could tell the user how many items are in the current vector and give them another chance to enter a valid value. That would be more user friendly than crashing the program due to a typo. When the program has a valid reference, the borrow checker enforces the ownership and borrowing rules to ensure this reference and any other references to the contents of the vector remain valid. Recall the rule that states you can't have mutable and immutable references in the same scope. The rule applies in listings 8-6 where we hold an immutable reference to the first element in a vector and try to add an element to the end. This program won't work if we also try to refer to that element later in the function. Compiling this code will result in this error. The code in listing 8-6 might look like it should work, but why should a reference to the first element care about changes at the end of the vector? The error is due to the way vectors work. Because vector puts the value next to each other in memory, adding a new element onto the end of the vector might require allocating new memory and copying the old elements to the new space. If there isn't enough room to put all the elements next to each other where the vector is currently stored, in that case the reference to the first element would be pointing to deallocated memory. The borrowing rules prevent programs from ending up in that situation. To access each element in a vector in turn, we would iterate through all of the elements rather than use indices to access one at a time. Listing 8-7 shows how to use a for loop to get immutable references to each element in a vector of i32 values and print them. We can also iterate over We can also iterate over mutable references to each element in a mutable vector in order to make changes to all the elements. The for loop in listing 8-8 will add 50 to each element to change the value. Oh yeah, this is nice. To change the value that the mutable reference refers to, we have to use the star dereference operator to get the value in I before we can use the plus equal to operator. We will talk more about the dereference operator in the following. The pointer to the value with the dereference operator section of chapter 15. Iterating over a vector whether immutably or mutably is safe because of the borrow checkers rule. If we attempt to insert or remove items in the for loop bodies in listing 8-7 and listing 8-8, we would get a compiler error similar to the one we got with the code in listing 8-6. The reference to the vector that the for loop holds prevents simultaneous modification of the whole vector. Using an enum to store multiple values, vector can store values that are of the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need one type to represent elements of different types, we can define and use an enum. For example, say we want to get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating point number, and some string. We can define an enum whose variant will hold the different value types, and all the enum variants will consider will be considered the same type, that of the enum. Then we create a vector to hold that enum and so ultimately hold different types. We have demonstrated this in listing 8-9. Rush need to know what types will be in the vector at compile time, so it knows exactly how much memory on the heap will be needed to store each element. We must also be explicit about what types are allowed in this vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause error with the operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled as discussed in chapter 6. If you don't know the exhaustive set of types a program will get at runtime to store in a vector, the enum technique won't work. Instead, you can use a trade object, which we will cover in chapter 17. Now that we have discussed some of the common ways to use vector, be sure to review the API documentation for all the many useful methods defined on vect by the standard library. For example, in addition to push, a pop method removes and returns the last element. Dropping a vector drops its element. Like any other struct, a vector is freed when it goes out of scope, as annotated in listing 8-10. When the vector gets dropped, all of its contents are also dropped, meaning that the integer it holds will be cleaned up. The borrow checker ensures that any references to contents of a vector are only used while the vector itself is valid. Let's move on to the next collection, type string. So we will look string in the next video. Thank you for watching. Bye.